Quick review for GR4 for MATH356. Thank you, DJ, for this test, which is not under academic security, right? Until grades are released in Gradescope. This is fall 2023, so we assume grades have been released on Gradescope. And so let's go. I blanked all of it out, so we're gonna try and do it together. Hopefully I can answer these questions. Let's see. Bone mineral density, BMD, measured in gram per centimeter squared, is a great indicator of bone strength and a strong predictor of fracture risk. The bmd.csv file in the data folder contains various physiological measurements for 169 individuals. Use the provided RMD to answer the following questions. Fit a linear model to the data with BMD as the response. Okay, so I want to change color. Let's say response and weight kilogram as the predictor. So we're going to say response, and this is going to be not the predictor, the weight in kilograms. So they're saying that the weight in kilograms somehow, I don't know why I wrote the response, sorry. I wanted to write BMD. So bone mass density, right? Is that what it was? Bone mineral density. Bone mineral density, but it's not capitalized, so let's just be very precise. Bone mineral density as a function of weight kilograms, where this command, well, we want the slope coefficient, so we assume the slope coefficient of a linear regression, so we use the LM command here. That is coming from bone because they said interesting. I don't know that the data would be bone. According to this, is bmd.csv, or maybe they meant bone. For the summary, we're going to summarize our model. So we're going to summarize our bone model right there. And then if you input this into R, then you would get an answer for the slope. Now, I don't think I have the files for that, so let me just double check real quick. That would be math. Okay, I don't have it. So, assess the reliability of our linear model by examining the diagnostic plots below. Disregard the independence condition and thoroughly justify your answers. So here we see that the variance is not constant throughout. From residuals versus fitted, from residuals versus fitted, can be noted that the variance of the residuals is greater towards the center of the plot, comma, suggesting that the equal variance assumption used in the model may not be appropriate. Then normality of residuals, judging from the quantile plot, from the QQ plot, note the normality assumption assumption is met because most of the data points fall on the normal line. And then we have the residuals versus leverage. So, well, we have to think about the line acronym. Linear fit, the linear fit plot 1 is also fairly valid because the line passing through the residuals through the graph is straight, roughly straight. Okay, now generate a 99% bootstrapped confidence interval for the slope parameter of the simple linear regression model using resampling. So we want to do bone mineral density as a function of weight in kilogram, right? Weight in kilograms. But now we want to resample, so we want to do a bunch of LM, resampling the data. The data that we're resampling is bone, so we're going to put bone right here. And then we want a 99 bootstrap, so I know I have to put a 99 there. And here, the data is bone boot, as you see right there. And what do you have to put here? Here we have to put the explanatory variable because we want the slope with respect to that variable. And then we're going to get the confidence interval. Now this is a confidence interval on the slope. Which one of the following statements is true about the potential drawback of resampling using a bootstrap method? Well, let's think about it. In a bootstrap method, if you resample the observations overall, so both your explanatory variable and the results from your response variables, then you might incur into influential points that are sampled in some sampling of the bootstrap and not sampled at all in others. So resampling relies on a strong assumption of the normality of residuals. This might not always be the case. No, this would not be true because bootstrap does not assume normality. It's actually a way to not have to assume normality, to get around that assumption. Resampling may lead to the duplication of influential observations in some resamples, thereby increasing sensitivity to outliers. I like that one. That's kind of what I was saying. Now, the procedure of resampling does not guarantee accurate prediction since it ensures only small residual values are represented in the data. No, all residual values can be sampled, sorry. All residuals values can be sampled. So that's why I would discard this one. The procedure of resampling does not guarantee accurate predictions since it ensures only large residual values are presented in the data. And now, again, I would refer you back to that statement. Okay, now, execute the code in the provided RMD to add a column to your bone dataset, calculating the body mass index for each observation. Using the regression output below, which one of the following interpretations is false? Please fully fill in the circle corresponding to your chosen answer. Well, let's see what we have here. So we have body mass index as a function of weight, and I think they did the body mass index for us. Yeah, provided in the RMD. And we have the data coming from the bone data set. Here we get a bunch of things about the residuals. So the median residual, the first quartile, the minimum residual, the maximum. And then here we're talking about the coefficients. So we have weight here with this slope and the intercept with this value right here. Okay, now let's see. According to the model, on average, an individual with a body mass weight of 0 kilograms would have a BMI score of 4.60. Well, what would be our model? Let's write it down. BMI equals 4.6 plus 0.32 times weight in kilograms. Okay. Well, let's see, would that be good, a good interpretation or not? An individual with a body weight of 0 kilograms, so when this is 0, would have a BMI score of 4.6. Well, that seems reasonable, right? But would it make sense that you have a body mass index of 0 if you weigh 0 kilograms? Well, if you weigh 0 kilograms, you don't exist. So I'm not sure that this would be correct. Let's cross it out for now. It'd be correct in terms of the model, but it's an extrapolation. This is an extrapolation because we're saying something, we're trying to predict something that is outside the observed predictor range. For every additional kilogram added to an individual's body weight, the average body mass index score is expected to rise by 0.319. That seems reasonable to me. I like this one. So let me bubble this one for now. For every additional kilogram added, the average body mass index score is expected to rise. Now, is it the average body mass score or is it the true body mass score? I think it doesn't make a difference in this case, but I'm not sure. There's always confusion between the true value and the average value in these scenarios. On average, the predicted BMI values from the linear regression model have an error of about 1.07 units when compared to the actual observed BMI values. On average, the predicted BMI values have an error of about 1.07 units. Well, 1.07 units, this is the standard error of the intercept. Or, yeah, I'm not sure that this is right. The observed correlation between BMI and weight is 0.833. Well, to know the correlation, you would have to take the square root of your r squared if you have a simple linear regression. Which would be what? Would be the square root of 0.6942. That seems right also. So I think this is dubious because for every additional kilogram added to an individual's body weight, the average BMI score, maybe it's not an average BMI score, it's the specific BMI score. I don't know, for some reason this is not right, probably. Because I know that this is right, because remember that for a simple linear regression, R, the square root of R squared is correlation. But that's only when you have a single predictor variable, which is what simple linear regression implies. Now, suppose your aim is to examine whether there is compelling evidence in the data indicating an association between BMI, body mass index scores, and body mass D scores. I don't know what D stands for. Using the regression output below, state the null and alternative hypothesis of this inference analysis. Well, so the first thing I would ask is, there's compelling evidence indicating an association. Well, it's because there is one intercept, then this value will be the same as that value. We can say the null hypothesis says that beta 1 is equal to 0. The alternative, beta 1 is not equal to 0. So in words, the null hypothesis would be there is no linear association between BMI and BMD. And the alternative is there is linear association between BMI and BMD, or in other words, there is a linear correlation, a positive correlation, or there is a correlation or not. Based on the regression output, provide the conclusion of the hypothesis test and offer an interpretation of what this implies in the context of this scenario. Well, I'm not sure what BMD is. Let me see if I can find this somewhere else. BMD, no. I'm not sure. You would have to put question mark bone into your R studio, and there you would get information about the data. But based on the regression output, provide the conclusion. Well, this is very, very small, so we conclude that that BMI has predictive power with respect to BMD. So that there is a relationship between BMI and BMD, and that the latter has predictive power with regards to the former as an explanatory variable for a linear regression. And again, I don't claim this to be the best wording or the best way to answer the question. This is how I would personally do it. So just don't think that whatever I say has to be correct. Build a multiple linear regression model with BMD as the response. So we know BMD is the response. BMI plus age plus weight in kilograms plus height in centimeters are the predictors. Using the output from R, how much of the variability in the response variable is explained in the predictor variable, by the predictor variables? Well, that would be, again, using the output R, but adjusted R squared because you have multiple predictors. And so you would put your value here. Or we put here bone mod 2. Now, based on the summary output from part A, the p-value for the F hypothesis test is less than 10 to the negative 16. What are the null hypothesis and alternative hypothesis? So the null hypothesis is that all the coefficient B1, B2, how many do we have? 1, 2, 3. B3 are equal to 0. And here, the alternative is at least 1 is different. Now, this is close to the ANOVA test. The only difference is that here we're saying that these values for the coefficients are equal to 0 instead of to a specific value, even though you could argue that 0 is a specific value. And so at least 1 is different just tells you that at least 1 has predictive power in terms of the variable that you included, but it doesn't tell you which one. So keep that in mind as you keep going and keep studying this. Now, here's another thing we have to talk about. Using a significance level, not a confidence level, a significance level of 0.05, which predictor variable would you remove first from the multiple linear regression model? Well, whatever has the smallest p, the largest p-value, which I can't see right now. Now, given your multiple linear regression model, construct a 90% prediction interval for the bone mineral density of an individual with a body mass index of 18.4, an age of 60.25 years, and a weight of 66.5 kilograms and a height of 180 centimeters. Show your work by completing the code below and rounding the results to 3 decimal places. So we want to predict, well, they already put everything in, which is interesting. They want us to predict, I'm not sure what to put here. I think we need to use our model. So I will put my model in. I'm pretty sure we need to put the model in. So what was the model number? Bone mod 2, the one with the different predictors. So bone mod 2, and then you get a confidence interval. You want the level to be 0.9. An interval should be confidence, not prediction. I don't remember what the wording is specifically if it's not confidence. So there's something to look up. What is the counterpart? Prediction or predict? I don't remember. And Mary Sue, driven by pure enthusiasm, computed the following 90% confidence interval from the body mass density, I don't know what BMD stands for, of an individual using the same multiple linear regression model and predictor values as mentioned in the previous problem. Which interval the confidence or prediction is wider and why? So the prediction is wider because it is the expected value for an individual in the population with the specified with the specified predictor variables. The confidence interval gives an average value and therefore has less variability. Great. Now, the variable fracture is a binary variable such that an individual who experiences a bone fracture is assigned a value of 0 or is assigned a value of 1. An individual who has not experienced a bone fracture is assigned a value of 0. Fit a logistic regression model where fracture is the response variable. Okay, GLM is the command that you would use. Fracture is the response variable with BMD plus BMI. Family binomial because the prediction is either you do have a fracture or you don't. For a unit increase in BMI, the log odds ratio that the individual has experienced a bone fracture decreases. Well, I don't have the model in front of me, but in general, we would say for a unit increase in BMI, the log odds ratio, so it wouldn't be the probability. For a unit increase, the relative risk that the individual has a history of a bone fracture goes up by, I'm not sure that this is the right one. For a unit increase, the odds that the individual has experienced a bone fracture increases by, it's not the odds, it's the log odds. So I think it's this one. Given the confusion matrix for the actual and predicted results from the logistic regression model, report the accuracy of the model as a percentage. Show your work code for full credit and round your answer to 3 decimal places. Well, okay. So we know we have 110 plus 33. These are correct because the actual was, yes, they had a bone fracture, and the result of the prediction was, yes, they had a bone fracture. Here, the actual was, no, they didn't have a bone fracture, and the prediction of the result of the prediction was, no, they don't have a bone fracture. And everyone else was an error. So my percentage is 110 plus 33 divided by 110 plus 33 plus 17 plus 9, which gives us, let me just do it, 110 plus 33 divided by 110 plus 33 plus 17 plus 9, 84.6%. But now they want to 3 decimal places, so let's give them 1.5 as well. $84.615, which is the same answer that DJ got. Great. Well, I hope this was a useful review for you. It definitely was for me. And I wish you good luck.